everyone. This one's going to be a little bit different. We're doing lesson 8.2, interpreting graphs of exponential functions. Right after this lesson, after you're finished with your notes, you're going to go straight into the McGraw for this assignment. You are going to do this assignment in your book, not in your notebook, because there's way too many things to write for in your notebook. So we're going to interpret exponential functions today, okay? Recall that exponential functions are in the form of y equals a times b to the exponent x. They're called exponential growth functions if a is greater than 0 and b is greater than 1. They're called exponential decay functions if a is greater than 0 and b is between 0 and 1. So we can learn a couple of things here. With growth functions, the domain and range, okay? The domain is all real numbers. Domain is that x value, so my left, right. Range is my up, down value. My range, y is it's gonna be all numbers greater than 0. So range is my y, okay? So in exponential decay functions, my domain, my x, is also gonna be all real numbers, and my y is going to be everything greater than 0. So intercepts. For exponential growth, they're going to have one y-intercept and no x-intercepts. For exponential decay, you're going to have one y-intercept and no x-intercepts. In behavior, for growth, as x increases, y increases. As x decreases, y approaches 0. So remember, end behavior, we're looking at the end by the arrows. For exponential decay, as x increases, y approaches 0. As x decreases, y increases. So let's do an example. Example 1. This is the first page that yours is on. This is on page 71, and this is page 72. Okay? So each time you fold a piece of paper in half, it doubles in thickness. If a piece of paper is 0.05 millimeters thick, then you can determine the thickness y of a piece of paper given the number of folds x with this function, y equals 0.05 times 2 to the x power. Analyze and graph the function, then find and interpret, that's what we're doing right now, we're interpreting the key features, including any constraints on the domain and the context of the situation. So let's first figure out, is this exponential growth or exponential decay? So if I look at, here's a, here's b, and then there's x. I'm worried about, is a greater than 0? Yes, it is. So now I look at b. b is greater than 1, so therefore it is exponential growth. Okay? The next step is to graph the function. That's it. Take this, choose some numbers to plug into x, and get numbers for y. Easy one, 0. If 2 to the 0 power turns into 1, so 0.05 times 1 is 0.05. I'm going to go ahead and graph everything that I do. So I've got 0, 0.05 up here. Oh, that's 0.5. Okay, I was right the first time. It was right there. Now let's do it if it's 1. If it's 1, it stays the same. So this is 2. And then I've got 2 times 0.05. So 0.05 times 2. 0.1. 0.1. So I'm going to go over to 1 and up to 0.1. Now notice I'm starting to get a curve here, so I want to do at least one more here, and I probably want to do one down here too. So I'm going to do 2 to the negative 1, which is 0.5. And then I'm going to multiply that times 0.05 times 0.05. Oh, got too many. 0.05. There we go. So 0.25. 0.025. So that is actually, so negative 1 and 0, I should write it down, 0.25. So that is slower than that. So negative 1, it's going to be almost right on the line. Okay? And then if I do it again, because I just want you to see where that line is going. If I do 2, see it? to the -2 power, get the 0.25, and then I'm multiplying it times 0.05. I get, oh look, it's even smaller. So it's getting even closer to that line, but it kind of evens out. 0.0125. Okay, I need to come up here and do this one though. I know that 2 to the power of 2 is 4, or you could go 2, 2. It's 4, and I'm going to multiply that times 0.05 times 0.05. 0.2. So at 2, I'm going up to 0.2. So you notice I'm starting to get my curve. You can do as many of these as you want. Really, I could draw my line now, but it might not be exact for what they want. So I'll just keep doing this for your guys' sake. Got 2 to the power of 3, which is 8 times 0.05, 0.4. 0.4. So I've got 3, 0.4. So 3, 0.4. Notice how I went up. Now I'm plugging in 4 for the exponent. So I've got 2 to the 4th power. And then I multiply that times 0.05. And I get 0.8. Notice how it jumps each time a lot? That's why they're exponential functions. So this time it gets smaller and smaller and smaller and smaller, but never reaches 0. And this time it got larger and larger and larger. It kind of evens out right there. Not very good at drawing lines, as you know. Okay. Now let's interpret the key features of the graph. The y-intercept, so right here, where it meets y, is 0.05. So the thickness of the paper before it has been folded is 0.05 millimeters. The thickness of the paper is, as I'm going this way, it's always getting thicker, so it is always increasing. Okay? The thickness of the paper is, did it ever go down to the negative? No, so it is always positive. Because the number of folds cannot be negative and must be counted in integers, the potential relevant domain is the set of whole numbers. However, the paper cannot be folded indefinitely, so the relevant domain is restricted to the greatest possible number of, how many times can you fold it? So only how many times that you can fold it. Because the paper has a starting thickness of 0.05 millimeters, the potential relevant range is all numbers greater than or equal to, well, how thick can the paper get? It starts at 0.05, so it can't be any thinner than that. However, the thickness of the paper cannot grow to infinity, so the relevant range is restricted to the greatest number of folds. So it's the greatest thickness. The greatest number of folds gets us the greatest thickness of the paper. Asymptote. The asymptote is 0. Y equals 0. So the thickness of the paper must be greater than 0 millimeters. Because y equals 0.05 times 2 to the x power is an exponential growth function, as x increases, y increases, and as x decreases, y approaches 0. Within the relevant domain, as the number of folds increases, the thickness of the paper will also increase. Now I know you're a little bit like, this was a lot, Ms. Watkins. It's okay. We're going to do another example. We're going to do an example of an exponential decay function. So we're going to do the exact same thing that we just did with exponential decay. Okay, so I'm now flipping to page 74. Okay, the half-life of a substance describes how long it takes for the substance to deplete by half. The half-life of caffeine in the body of a healthy adult is approximately 5 hours, meaning that it takes 5 hours for the body to break down half the caffeine. Suppose an energy drink contains 160 milligrams of caffeine. The amount of caffeine Y left in your system after about after X about 5-hour periods. This is modeled by the function y equals 160 times half to the x power. Analyze the graph of the function and then find and interpret the key features, including any constraints on the domain and context of the situation. So part A, is this exponential growth or exponential decay? That's greater than 0. That is between 0 and 1. So this is going to be an exponential decay function. Okay? Part B is graphing it. Let's go ahead and do the easy one. If x is 0, that means this is 1, so the answer is 160. So at 0, we're going to jump all the way up to 160. Okay? I don't even want to do the negative one because I'm not going to go this way, so I'm just going to keep going forward through the positive ones because look at my graph, I can't go to negative 1. So if it's 1/2, we know it's the same, right? I'm going to use 0.5 for 1/2 because we know that 1/2 is 0.5. So 0.5 to the 1 power is still 0.5. I'm going to multiply that by 160. It's 80. Oh, look, half of 160 is 80. So at 1, I'm jumping down to 80. We're going to see this curve being made. So now I'm going to use 0.5. I'm plugging x in, plugging 2 in for x. So 0.5 to the 2nd power. And then I'm multiplying that times 160. I get 40. So at 2, I'm going to be at 40. Now these numbers, you just make these numbers up. I usually 0, 1, 2, sometimes a negative 1. That's how we get our curve. And we're plugging them in. Remember, this is x. That's where I'm plugging these numbers in at. Do the next one. 0.5 to the 3rd power. Get it where you can see it. There we go. And I multiply that times 160. 20. Notice how far down we're going. On 3, I'm going to be at 20. Let's do one more. 0.5 to the 4th power. And I multiply it by 160. It's 10. So at 4, I'm at 10, which is about halfway there. I can go ahead and draw that line. Or that curve. Now let's do this part. The y-intercept is, here's y, 0, 160. So the y-intercept is 0, 160. So immediately after drinking the energy drink, there are 160 milligrams of caffeine in your system. Because time cannot be negative, the relevant domain is everything when x is greater than or equal to 0, because time cannot be negative, and x is our time. For range, that's our y values, because the amount of caffeine cannot be negative, and the amount of caffeine when x is 0 is 160, the relevant range is between 0 and 160. So y is our range. Is between 0 and 160. So it can't be less than 0, but it can't be more than 160 because that's the amount of caffeine that was just drank. Okay? The asymptote is y equals 0. Okay, so here, x equals 0, y equals 0. Asymptote is y equals 0. So as time increases, the amount of caffeine in your system approaches 0. Okay? So you guys are just going to go ahead, and that should say 8-2. 8-2 graded practice. It's 4 questions. You're just trying to rationalize the problem. Ask for help if you need it. Miss Sunny and I and Miss Concannon are here. We'll work this out. Okay? Have a great day.